All right, we're going to talk about a little bit of pressure here. So, I mean, what do you want to say pressure is? It's kind of the ratio of the force, whatever force it is applied applied to the area. The force is applied to. I don't know. It's kind of like how dense a force is. It's kind of a force density in a way. So it's the symbol for pressure is P, and the units are called Pascals, which is the same thing as newtons per area square meters. And so you can say that pressure is the force divided by the area that the force applied to. So P is F over A. Or you can write it as F equals P times A, depending upon whether the force determines the pressure or the pressure determines the force. It's kind of tricky, with water applying pressure, the pressure and the area are separately determined. That determines the force the water exerts. When you're talking about a solid, usually the force is determined and then the area together make the pressure for a solid, Right. Why can a tomato be cut in half by applying force to a knife? The same force to a baseball bat will not cut the tomato in half because the knife edge has a tiny area. Okay, the knife edge has a tiny area, so pressure equals force over area. So same force on the tiny knife edge area results in a much greater pressure, and that's what actually cuts the chemical bonds that hold the tomato together, right? Okay, so how do randomly moving molecules in a liquid or gas cause pressure? Well, what happens is that the randomly moving molecules exert a force as they bounce off. So as they randomly move, they bounce off, and as they do, the wall exerts a force on the molecule. Right, that makes sense because the molecule doesn't move in a straight line with a constant speed. If the direction changes, there must have been a force. It's Newton's first law, right? If the wall exerts a force on the molecule, then the molecule exerts a force on the wall. That's Newton's third law. So just have your students kind of explain that here, that the molecules bounce off the wall, and if the wall exerts force on the molecule, which way does the wall push the molecule? It's got to be out because that's a normal force. But then the molecule exerts a force on the wall. All those forces from all those collisions divided by the area determine the pressure, right? Okay, so a balloon is inflated by causing air molecules enter the balloon, i.e. blowing up the balloon, right? Explain in terms of molecule why the balloon's volume increases because the molecules collide with the inside edges of the balloon, right? And push out on the balloon rubber, right? Or something like that, right? That's the idea. They push out on the balloon and the balloon expands. Okay. Then we place the balloon into a chamber and we remove the air from the chamber. Why would the balloon's volume increase? Well, here's the reason is because the outside air pushes in on the balloon, right? Okay. Removing the outside air, you remove the inward push, but the outward push from the inside air remains. So if you have a balloon with air molecules from the outside pushing in and air molecules from the inside pushing out, if you take away the outside air, then the inside air is still pushing out and it will expand the balloon, right? Okay. Let me show you this thing called a suction cup lifter. This is something that I got from Harbor Freight Tools. So Harbor Freight Tools, 4.5 inch suction cup lifter. And the way it works is when you clip this like so, let me back the camera up a little bit. Maybe you can see this better. When you do this, it's just it's a little spring-loaded mechanism. I don't know if you can see that spring in there. Do you see that? But can you see this when it's black? Watch. It pulls and it makes this into a bow shape. Well, if I put this onto a table and I do this, it creates a evacuation here where there's no air, and then it won't move it freaking all, right? And then I got to unstick it, right? So I could do that onto this clipboard with a dry erase surface I got from Amazon. You can get them in like packs of 30. They're really good for your students if you want to do whiteboarding. And I do this, and then, I mean, it's stuck on there really good. In fact, if you don't believe me, then check this out. Okay, that's a little rolling desk in my classroom. You'll see all of my lab tables are fixed in place, but because I have overcrowded classrooms, which I know is rare in education to have overcrowded classrooms, right? Well, I'm going to stick this on here. So there's only air and very little of it between this rubber and this surface, and yet I'm able to lift up the entire desk pretty much completely off the ground, right? So that's a great little demonstration you can do with your students. If you want to buy one of these from Harbor Freight Tools. So I want my students to understand why that happens. I want them to be able to explain it. So what they're going to say, and you can coach them through this, right? I don't expect my students to get it on their own, but at least what they see. So the idea is that the suction lifter is lifting up an entire table, which is what I did back in my old school where I had a table I could do this. And I wanted students to draw arrows representing the air pressure on the suction cup and the table. So I might draw 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 arrows on the top. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 arrows on the bottom. If you want to draw arrows on the side, just for good measure, but that's all those arrows cancel out. And because they all cancel out, the free body diagram you draw is just pretend like this is connected to a rope, the tension in the mg, and all the up and down air molecules that cancel out. Well, what if I only look at just the suction cup? Then it's only these 5 arrows right here explaining why the suction cup has, like when I lifted this up, it would be force tension and just the mg of the suction cup. And you'd think, like, look at this right here. Look in this little window. Look at how easy it is to lift it up, right? But when it's on the table, now it also has a humongous force of air, making it feel sufficiently heavier. So you see the goal of what I'm doing here is I'm dividing this thing from a system to 2 separate objects. Now here's the 1, 2, 3. Here's a 1, 2, 3. And here's a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think it was 11, and then on the side, right? So what do you look here? What lifts up the table? That's why I want the students to take away from this, is what lifts up the table is the air underneath pushing up without matching air on the bottom pushing down. So here, what you have is you have the mg of the table and the force tension, but you also have oh, no, I'm sorry. You don't have the force tension because the force tension is not directly on the table. So you just have the force from the air. And just these arrows are unbalanced. The other arrows are balanced with each other, right? So how's the table not pulled down by gravity in this situation? Because the air pushing up on the bottom of the table is not balanced by the air pushing down on the top, right? Due to the evacuated, or whatever you want to call it, the vacuum that's in here. That's a vacuum right there. You see that? Evacuated volume under the suction lifter, right? This lifter is not even 1 Newton. This is not 100 kilograms. I just made up that number for the heck of it, right? Well, why is the tension of the rope 500 Newtons? Because there would be 499 Newtons of air pressure pushing down, right? There's 499 Newtons of air pressure pushing down, right? And on the lifter that is not matched or balanced, you could say, by air pushing up from underneath. So the reason the suction lifter, if you'll look in your window right now, here by the little window, hello, you see me? The reason the suction lifter only feels like it's a few tens of grams, maybe 100 grams, that'd be 1 Newton. Maybe this is 1 Newton. The only reason it feels that way right now is because there's a humongous amount of air pushing down on the top and a humongous amount of air pushing down on the bottom. Those balance. But if I make this area have no air, then I have all this air on the top that's pushing down, but not any air underneath. So this is all a discussion of looking at the suction lifter and the table as a system, then looking at the suction lifter and the table as separate objects. Okay, the diameter of the suction lifter is 4.5 inches. So that's actually about, so it's 11.44, not meters, but centimeters, 0.1144 meters. Right. What's the heaviest mass table that you could possibly lift? Well, here's what I'm going to do, is I'm going to say that area is pi times half the diameter for radius squared. So pi times 0.1144 over 2 squared. So I'm going to take this, I'm going to divide by 2. I'm going to square it. Oops, I didn't mean to do that. I need to do 0.1144 divided by 2. Then I'm going to square it. Then I'm going to multiply by pi. And so I've got basically 0.1. So I got 0.01 meters squared. Now, the air pressure is, it's 101,300 is the standard air pressure, 101,300 Pascals. I think this is on the AP Physics formula chart. Now that fluids is on there, at least the draft that I saw, it's on there. But in the past, they used to just ask students to use 100,000. Well, if it's 100,000, then force would be pressure times area. So that'd be 100,000 multiplied by 0.01. So just move the decimal place 2 places. And that's 1,000 newtons, which is the same really as 100 kilograms, which is how much I weigh. So if I was to sit in that desk, you would probably just barely be able to start lifting me with the suction lifter before it did actually come loose and the air filled in the gap, and then you just drop me to the floor. Isn't that crazy? Pressure varies with depth. This is being recorded shortly after the Ocean's Gate debacle. I'm just going to tell you that right now. I can probably tell about when it was recorded based on the shirt I'm wearing, right? So, so this is probably something that you're going to talk about with your students when you do pressure with depth, is the idea that the pressure gets pretty high pretty fast in water. So the pressure at a certain depth, the pressure at depth, so we call that pressure at depth. Well, you have to start with 1 atmosphere. Okay, this is 1 atmosphere because of the air pushing down on the top of the water, plus the density of the fluid, gravity, and H, which we use for the depth in the fluid. Now, I'm just going to make this note that that this is absolute pressure. Okay, so if gauge pressure is desired, right, you're going to omit the pressure of the atmosphere. So let's say you're talking about the Ocean's Gate sub. When the Ocean's Gate sub was at the surface, the pressure on the outside was the same as air pressure because it was in the air. It hadn't submerged in the water yet, right? But the air inside is also at air pressure because there are people in there. So we would want to talk about the gauge pressure. The gauge pressure at the surface is 0 because the inside air and the outside air are both the same pressure, which is 1 atmosphere. So there'd be no net effect of pressure. But as you go deeper and deeper and deeper, in fact, think about the numbers here. This is 1,000 and this is 10. So together these are 10,000. It takes 100,000 to make 1 atmosphere. So that's where the diver's rule of thumb comes from. The diver's rule of thumb is 10 meters, 1 more atmosphere. So every 10 meters you go down, that's 1 more atmosphere. So think about, like, what did they say the Titanic is? Like 4,000 meters deep. That's over, was it 4,000 meters? Is it that far? Because then that's 400 atmospheres, right? Isn't that crazy? This equation is only true for incompressible fluids, right? Which is like liquids specifically. You cannot use this equation for a gas. And the reason why you can't is because as you go deeper down into a gas, The higher the pressure changes the density. That's like your PV equals nRT from the ideal gas law. Well, you don't need to teach your students this in P1, but you may just mention them. Hey, the higher the pressure, the more moles there will be per volume, and that actually changes the pressure, the density. So it's a more complicated equation because this actually varies with pressure, right? They depend on each other. The force of a fluid is always applied perpendicularly into the surface the fluid pushes on. So this is like the opposite of the normal force, where the normal force pushes perpendicularly away. The pressure force, if you want to call it that, exerts force perpendicularly in on each side, right? Okay, gauge pressure ignores atmosphere. Gauge pressure ignores the pressure of the atmosphere. In other words, you treat the pressure of the atmosphere as zero, right? And the absolute pressure includes the pressure of the atmosphere. Okay, when do we use which one? Well, if you need a pressure difference, and the difference is between air and something else, like the Ocean's Gate sub, the inside pressure was 1 atmosphere for the people inside, and the outside pressure was hundreds of atmospheres, then you're looking at the gauge pressure, the difference. But the absolute pressure then, you would use for things like if you ever did AP Physics 2 and you did PV equals nRT, that's absolute pressure. Things like that. Okay, family drives from Colorado Springs, Pikes Peak. Have you ever had this experience? The sealed bag of chips inflates as you go up to higher altitude. What's happening? Well, in going up, the bag is less deep in the atmosphere, right? It's closer to space where the pressure is zero, so it's less deep in the atmosphere. So there's less pressure, less external pressure, right? External pressure, right? So the internal air pressure pushes out the same, but the external air pushes in less. So don't let your students make the mistake of saying that the internal pressure pushes out more. It doesn't push out more. It pushes out the same, but the external pressure is not pushing out as much, okay? 1 atmosphere in Pascals, 101,300 Pascals. You can round to 100,000 Pascals if you want. Okay, how deep must a person dive before the pressure equals? We talked about this. So pressure equals, this really should say the gauge water pressure equals 1 atmosphere. So 100,000 equals 1,000 times 10 times h. So the height, the depth is 10 meters. What is the total downward force exerted by air pressure on a square that's 18 centimeters wide? Let me just tell you, a lot of students do this demo with this suction lifter using an actual rubber base, like baseball, you know, the rectangular bases, the square ones. They'll drill a little hole in it, and then they'll stick a mass hanger through the little hole, and then they will seal it down and lift it up. And that's their way of doing, well, this is, I thought, pretty cheap. So, and it's, you know, people use these things to move windows, right? You can see the spring in there, like I promised. Okay, so let's see. So what am I going to say? 18 centimeters on a side. So force equals pressure times area. So force equals pressure. Let's just make it 100,000. Oops, excuse me. Okay, and then times 0.18 squared. And so this winds up being 3240 newtons. And in case you're wondering, that's about 728 pounds, right? So if you use your base, your rubber base, with the hole in it and the hook through it, the hooked mass hanger through it, then you could lift up quite a bit more than me. I'm about 100 kilograms, 220 pounds. Okay, normal eardrum has this area. Okay, diver's eardrum can rupture a depth of 4 meters. So the pressure, and I'm using gauge pressure, because on the inside, this pressure is 1 atmosphere. On the outside, the pressure is 1 atmosphere plus density, gravity, depth. So I need just the difference in the two, right? If the two pressures are equal, then there's no net force. So I need the difference. So rho g depth, Okay, so rho is 1,000, G is 10, the depth is 4. So that's going to be 40,000 pascals, which is 40,000 newtons per square meter. Now, how do you convert this? Well, you got to do a little bit of dimensional analysis, right? You got to say, okay, well, 1 meter is worth 100 centimeters. But watch out, because the centimeters are squared, this conversion has to also be squared. So 0.55 is going to get divided by 100 and squared. So this is an area. The area is actually 5.5 10 to the negative 5. Okay, so the force, pressure times area, that's the pressure is 40,000 times 5.5 times 10 to the negative 5. So let's multiply this by 40,000. And what's going to come out from that? It's going to be about 2.2 newtons. All right, so about 2.2 newtons, which I don't even know what that is. That's like half a pound. It takes about half a pound in order to rupture your eardrum. So be careful with that Q-tip. Okay, Pascal's principle says that if you, in a closed, so we have to start with this caveat, in a closed container, okay, so the container has to be closed. Otherwise, the fluid will spew out if you do this. Any increase in pressure at one point in the fluid results in the same increase in pressure at all points in the fluid. So what does that mean? Well, it basically means that this is how a hydraulic lift works. So I don't know if you've ever seen a Cartesian diver. I haven't built one. So look it up on YouTube. It's called Cartesian diver. And what it is it's a little thing with a little bubble in it. It's quite easy to make one with like a dropper. And then you put it in a sealed soda container. When you squeeze the soda container, you increase the pressure at one point in the fluid. So the pressure everywhere, including in the dropper, in the bubble, also increases. So that compresses the bubble, and it makes the Cartesian diver go from being less dense to more dense than water, and it will fall. Okay, so how does a hydraulic lift work? Here's how it works, is that you exert a small force over a small area, okay, and this result, a small area sealing a fluid. So in other words, there has to be a fluid on the other side of your small area. This results in a large force applied to a large area by the fluid. So what do I mean when I say this? Here's a basic schematic of a hydraulic lift system. And the idea is that these two pressures, P in and P out, are the same. So that means that the input force over the input area equals the output force over the output area. So the output area is a big piston that might be connected to a car to lift it up. The small piston is the input area right there. So if the output area is 100 times bigger than the input area, that's only 10 times the radius or the diameter. If it's a circular piston, then you get 100 times as much force out. So I'm going to use this idea here. Hydraulic lift consists of a large piston 5 meters, over a fluid small piston 1 meter. The container of fluid is closed by the pistons. Okay, if the car of mass 1250 kilograms on the large piston, what's the smallest a person can stand on the small piston and be able to push it down and make the car go up, right? Well, I said force input over area input equals force output over area output. Here's what I'm going to say. The force input is the little mg of the person, and the force output is the big mg of the car over the area, the small area and the big area, right? The g's cancel, and now what do I get? I get m over this area equals 1250 over this area right here. That's the kilograms. What are the areas? Well, it turns out that whenever you set up a ratio, you don't have to do pi r squared because the pi cancels. Well, don't you have to convert these radii to diameter radius? In fact, if it just said diameter and diameter of 1 meter, you would just say this. You just say, okay, this is 1 squared and this is 5 squared. In any ratio or anti-inverse ratio, area can just be, you can just plug in length squared as long as the two areas are similar, like a circle is similar to every other cylinder, right? A circle is similar to every other circle. So the pi's cancel out, any unit conversions cancel out, and you just get m over 1 equals 1250 over 25. So 1250 over 25 is 50 kilograms. So a 50 kilogram person could lift up this car. But here's the deal. The other thing that stays the same is this volume. If this volume is how far down this piston goes, then this piston goes up by the same volume. This volume is the same as this volume. How do you get volume? Volume is area times height. So the area on the input side times the height that the input person goes down is equal to the area on the output side times the height that the output side goes down, right? Okay, so those are the same. If the car rises 1 meter, and remember, this is basically 5 squared. Okay, hold on a second. The light turned off, so I have to walk around. Okay, so then this area right here is 1 square. What about the pi, Friendly? It would cancel out anyway. What's the height that they have to go? So this might rise up 1 meter, but they're going to sink into this well 25 meters. That's taller than my school. So then the input height would have to be 25 meters. And can I just tell you that you would have arrived at this also if you just multiply both sides by P. The P is the same, remember, that's Pascal's principle. Then you get force. Force times height. Force times height equals force times height. Kind of like force times distance equals force times, like the work is the same. The work that you put in is equal to work you get out, and you find out that a hydraulic is actually a simple machine. A hydraulic system is another simple machine where the input work has to equal the output work, assuming it's perfectly efficient. Okay, let's move on to some problems here. The pressure here and here have to be the same because both points on the dotted line have the same amount of water, which is dark gray. That's the water's dark gray. The oil is light gray below them. So because there's the same amount of water down to the bottom here and the same amount of water down to the bottom here, then the pressure here equals the pressure here, right? Now, what am I going to say then? I'm going to say, how do I going to know the density of the oil? Well, this pressure equals this pressure. Well, what is pressure? Rho GH. It's actually rho GH plus P atmosphere, but in a moment you'll see that the P atmosphere cancels out anyway. So it's the rho of the oil, G, this height. So the density of oil, G height, equals the rho of the water, G, this height. Now remember, if I put plus PATM here and plus PATM here because of the air pushing down here and the air pushing down here, well, that would cancel out because it would subtract. In fact, now the G divides out. So you just get the density of oil times the height. And what is the height of here? This is 0.4. And then that equals the density of water times the height of the water, which is 0.1. And then you get the density of the oil is 250 kilograms per meters cubed. Do you have the guts to actually set this up? I know I don't. And the reason why is because I hate oil. If it spills, it's so difficult to clean up. But it's the one thing that doesn't mix with water. So do you want to get some clear plastic tubing from Home Depot that's used in plumbing or refrigeration? Then maybe you can gingerly tape it to a plank of wood or something like that, like a particle board or a plywood board, and then set it up and then pour in some water and then pour in some oil carefully, very, very, very slowly on one side, and show the students this idea. That's up to you. Okay, if this force is 10 newtons and this diameter is 2 centimeters, this diameter is 8 centimeters, then Pascal's principle, force over area equals big force over big area. This force is 10 newtons. This area is 2 squared. Wait a minute, Friendly. You didn't shut up, okay? This force is what I want to know, 8 squared. Well, wait a minute, Friendly. This is centimeters. Doesn't it have to be converted to meters? The conversions cancel out on both sides. Don't you have to convert that to radius? No, that would cancel out on both sides. What about the pi's? They would cancel out on both sides. So in any ratio or inverse ratio, if you just plug into both areas, length squared, it works every time. So 10 over 4, F over 64. Another thing you could just say is that 4 times the diameter is 16 times. So this is 16 times the area. So it's going to have to be 16 times the force, which is 160 newtons. There's some YouTube videos that you'll find of people who have this trick, and I could never get it to work. They fill a beer bottle. Sorry, you have to be careful. You're going to be talking to high school students. They fill the beer bottle all the way up to the tippy top. So it's even bowing out because of the surface tension. And they've learned this trick where if they hit the top of the bottle in just the right way with their palm, it actually shatters the bottle from underneath. And that's because of Pascal's principle. I don't know the name of that trick, but you maybe find a beer bottle breaking trick. Look that up on Google. Okay. This person has 100 kilograms of mass. They're on an air mattress. The area is 2 square meters. And then the pump has this tiny cross-sectional area of his little pipe. Do you see that right there, the little tube there? So how much force must be applied to the pump to force the air in the mattress? So again, the tiny force over the tiny area is equivalent to the big force over the big area. Now, the force of this person is mg. So their force is 1,000 newtons, and they're lying over 2 meters squared. Remember, the area is just 2, not 2 squared. It's just 2 meters squared. Your student's going to be confused by that. And then force, and then this is 0.001. So if you cross multiply that over, you get a force of half a newton. And that's why it's so easy to push that pump. It's easy to push that pump, but watch out. If the pump is pushed down 1 meter, how much does a person ride? I'm going to use force times distance on the person end is equal to force times distance on the pump end. On the person end, it's 1,000 newtons and d distance to rise. On this end, the pump is half of a newton and it rises 1. So if you divide that right there, I mean, that's 0.5 divided by 1,000. That's like, 0.0005 meters. So what does that mean then? That means that to make the person rise up several centimeters, you got to pump. So on the person side, you get a big force, but he barely moves at all. On the pump side, you have a tiny force, but a big. So the Pascal's principle that goes into making a pump work is a simple machine. I really want students to take that. I want them to take that a hydraulic system, a pump system is a simple machine. Starting with this equation, perform a derivation to explain what the slope of pressure versus height represents. Okay, so if pressure is the Y and P naught is the atmosphere, I call it PATM. I think the AP Physics formula chart calls it P naught. Then if this is X, then everything that multiplies by X must be slope, and this must be the intercept right here. So if you have pressure versus depth, H is depth, then the slope is density times gravity, and the intercept is the basically the atmosphere at 0 depth. I mean the pressure at 0 depth, right? Okay, the air pressure is a function of height above sea level. Interesting. Is shown in the graph to the right, which, by the way, this is taken from real data off the internet. Estimate the density of the air at about 9,000. Well, here's 9,000 right here. So what am I going to do? I'm going to take the slope just here. It looks like you go down 10,000 and you go over 2,000. So I'm going to say that rho g equals the slope. What was the slope? It would be down. And this is, by the way, absolute value, please. Okay. What am I doing here? Oh, it was 10,000 was the rise. And, wait, hold on a second. This is 2,000 is the run. So then rho times 10 is equal to 5. So the density would be about 0.5 kilograms per cubic meter. Just so you know, you can look up the density of normal air. It's about 1 kilogram per cubic meter. So up there on Mount Everest, you're talking about half of the density of air that you're used to, right? Suppose a tiny balloon that's less dense than air is released from sea level. The balloon is made of smooth and rigid space-age material, so its volume does not change. It encounters no errors. If the balloon is subject only to forces of weight and buoyancy, so you got to watch out for this question. This question you may actually need to come back to in the notes because you haven't talked about buoyancy yet. So the force of buoyancy is the density of the surrounding fluid times the volume underwater or in the fluid, which the balloon is fully in the atmosphere of the Earth. It's not partially in space or anything like that, times G. So here's the balloon. It has a force buoyancy, and it has an mg. And if it's less dense than air, than the surrounding air, then the force buoyancy is bigger. But as you rise up, as the balloon balloon rises, okay, as the balloon rises, what are we going to say as the balloon rises? The density of the fluid, which is the slope of the pressure versus height, it's actually rho times g, but let's just say, decreases. You see that here, the slopes decreases. So the force buoyancy decreases. So what that means is that the upward force is getting less and less and less. Well, what that's going to do is that means that the upward acceleration decreases, right? But then as long as the acceleration is upward, the velocity increases. So here's what a velocity versus time graph might look like, where the velocity is always increasing as long as the acceleration is up, and the buoyancy force is always bigger than the weight. But the acceleration, which is the slope, gets less and less and less as the force up, which is the bigger force, will decrease, okay? And then eventually the two forces will balance, and then if there's significant air resistance on the balloon, it will just stop at that height, and then eventually it'll deflate and pop and die. Okay, so that's the end of that. All right, that's a long section on pressure. I hope you can make it run pretty quickly because pressure is important, but it's not the big show. The big show for fluids is buoyancy and then Bernoulli. Everything else is an appendage to that. All right, I'll see you on the next one.